Okay, great. Second speaker is Sakura Schäfer-Nameki, Three-manifolds and topological order. Please.
Okay, thanks very much. Thanks to the organizers. I was just remembering this year, because we're doing another meeting of a similar size in Oxford, how traumatic the 2019 organization of this conference was. So I really appreciate how much effort you put into it, and it's a lot of effort. So I thank you all for doing this. So it's a little difficult to give this talk at the end of the conference when essentially every other talk has been on the symmetry TFT, and that's been your sort of bread and butter for the last year. So what I actually decided to talk about is this very peculiar paper that we wrote in March this year with Federico Bonetti and Jingxiang Wu. Both of them were postdocs at the time when we started, about 2 years ago, thinking about this problem. And finally, we've put out the first paper, and there's some work in progress. And it's about geometry, but not of Calabi-Yau's, but of three manifolds and sort of topological phases. And I'll start a little bit sort of zooming out and talking about what people in this whole symmetry category sort of field have been up to in the context of topological phases. So one of the questions that you can ask as a high energy physicist, as a condensed matter theorist, as a quantum computing person, how do we determine actually IR phases of quantum systems, and preferably in the presence of some symmetry? And here symmetry for me will always be some kind of finite categorical symmetry, so it'll not be some continuous symmetry. So for standard symmetries, the answer to this question is Landau. Essentially, sort of, phases are characterized by some order parameters picking up a VEV, their charge and their symmetry, and second order phase transitions are such kind of symmetry breaking transitions. But it's also known that in fact not all transitions are actually given in terms of sort of this type of paradigm. So they're beyond Landau type phases. So one example are these deconfined critical points, but there are many others. So one conjecture or hope is maybe restricting to groups, group-like symmetries is too, too classical, too limiting. In fact, we should extend it to all possible type of symmetries. So in 2024, that would be like a generalized categorical symmetry. So this updated version of Landau would say, explain basically all the phases and transitions between these phases by using some suitably generalized symmetry. So what's sort of been emerging in the last year is that you actually can do this very beautifully using the SymTFT. So you've heard about the SymTFT from many, many speakers, but this is a slightly different application of the SymTFT. So the SymTFT is, you start with a symmetry S, think of it as your favorite symmetry structure. It can be a fusion category symmetry, it can be a non-invertible symmetry in higher dimensions. And then the analog of this question, what are sort of the spontaneous symmetry breaking phases and also symmetry protected phases? That's actually sort of generalizing this subgroup SPT phase classification for groups. That actually the answer to that is the SymTFT. So you can use the SymTFT to actually essentially classify the gap phases or topological phases in the presence of these categorical symmetries. And one other important question in this context is, of course, what are the order parameters? So what's the analog of a charged operator getting a VEV? That's actually replaced by generalized charges. And generalized charges, again, you've heard, are the topological defects in the SymTFT. So one application is classify all gapped, so topological phases with a symmetry S in D dimensions. And for this, you just need to run through this program, construct the SymTFT, and I'll explain to you how you actually, what you need to do to actually really carry this out explicitly. So in 2 dimensions, this is completely explicit. You can hand me your favorite 2-dimensional symmetry. It should be sort of simple, so it should have only finitely many generators. And we can construct then the SymTFT for this. And now the SymTFT, actually this is one slide too many. So the gap phases are precisely constructed in the following way. So you have the SymTFT. This is these 2 plus one dimensional theory. It's topological. There's two boundaries. This is the symmetry boundary. That's where your symmetry generators live. And normally here you place your physical theory. In all the other talks, or most of the other talks, this was some QFT, either generated by geometric engineering or in some other way, holography. So in order to get a gap phase, in fact, we place here also a topological boundary condition. So in fact, once you collapse this interval, this sandwich, you actually get a topological field theory. So here we start with three-dimensional theory, for example, and get a two-dimensional topological theory, and the presence of that symmetry ensures that that's actually a symmetric phase. So in this way, if you apply this for group symmetry, you get spontaneous symmetry breaking, SPT phases, all encoded in this way. So essentially what you need to do is classify all the gap boundary conditions, the topological boundary conditions for this symmetry TFT, and then this collapse thing becomes a TQFT with that symmetry. So in 2 dimensions is completely explicit. There's been earlier results, of course, but I think the most systematic is using the SymTFT approach. And the order parameter come from topological defects that stretch between the two boundaries. So you've seen this picture also in Ibu's talk today, right? There was this sort of operator from the boundary into the bulk. So here, if it ends on the symmetry, it means it'll talk to the symmetry on this localized here. And here, this means it's actually also in the resulting physical theory. And so this is sort of constructing now, for example, order parameters for non-invertible symmetries. One other nice thing is that this formulation allows you to also now go beyond sort of gap phases. So you may not care for topological theories, but you may care for transitions between two gap phases, and those are gapless phases. And so you can actually upgrade this sort of SymTFT to this sort of double sandwich or club sandwich, where you have an interface between two topological orders. And then in this way, we can construct transitions between two gapped phases. So in 2 dimensions, completely explicit, there's no geometry, so I can't really talk about this, but I wanted to give you an example, just to give you a flavor of how sort of unexpected certain effects in these sort of non-invertible symmetry studies are. So this is sort of the simplest phase diagram for the symmetry rep S3. Rep S3 is the fusion category symmetry for the permutation group on 3 elements. It has generators that are the irreps, the identity, the sign, and the 2-dimensional rep. And the tensor product is the fusion. And when you do the tensor product decomposition into irreps, you find this non-invertible fusion. That's sort of the simplest way of thinking about a non-invertible symmetry. Now you can ask, what are the gap phases for this symmetry? And this will not be simply, oh, there's a group and a subgroup and stabilizers and so on, because this is non-invertible. Whoops. So using this SymTFT, we can actually construct all the gap boundary conditions. There are exactly 4 phases. They have 1, 3, 3, and 2 vacua. This is sort of the trivial phase, where the symmetry acts sort of trivially. That's sort of the symmetry preserving phase. This is the completely symmetry broken phase, the spontaneous symmetry broken phase. There's 3 vacua. And then there are some intermediate phases. This is basically just the Z2 symmetry breaking phase. There are 2 vacua, and the Z2 acts between these two. And this is sort of an intermediate thing, rep S3 mod Z2 SSB. And now this is just the gap phases. The vacua, the action of the symmetry indicated by these arrows can all be worked out from this SymTFT picture. And then the nice thing is, with this upgraded sandwich, this club sandwich, we can also now construct these transitions. So for example, this is just a Z2 symmetric conformal field theory. That's just the Ising CFT. On this side is a Z3 symmetric CFT. That's a Potts model. And then here there's this slightly more exotic transition between these rep S3 SSBs. It's Ising plus Ising 2 universe CFT. And now, of course, there's a multi-critical point that sits here in the middle. Okay, so that's just to give you a flavor of what type of things we have been up to in this sort of symmetric phase story. And that works, I think, in 2 dimensions really beautifully. In 3 dimensions, it's sort of a natural next step. You run into a slight sort of problem. So of course you can start again asking, is there sort of a symmetry breaking Landau type story? You start with some two fusion category, you pop out the SymTFT, you look at the gap boundary conditions. But what you notice is that in 3 dimensions, there's a little bit more than just sort of one form symmetry, zero form symmetry, two group symmetry breaking. And there's sort of this intrinsic topological order that's really sort of special to 3D. So this is sort of nothing you can sort of explain just by SSBs or SPTs of class sort of standard symmetries. So in that sense, 3D is particularly interesting. And one of the things I'd like to discuss is how one could take a slightly different perspective on classifying 3D topological order. So what is this 3D TO? Mathematically, it's characterized in terms of what's called MTCs, so modular tensor categories. Essentially, in terms of the boundary 2D CFTs, it's just the more Seiberg data for rational CFTs. So this is a fusion category C. It has finitely many objects, and these objects we should think of as line operators. These are the so-called anyons, so they can have kind of weird spins. They're not just bosonic or fermionic, they can be these anionic spins. They have a fusion given in terms of non-negative integer coefficients. And they're subject to various conditions. So let's call R the rank of how many lines we have here. Then there are actually two ingredients, the modular T and modular S matrix. So hidden in this terminology, these are modular tensor categories. The modular T matrix is basically what's called the spin of an anion. So that's a characteristic object associated to each line. There's some twist. And there's a diagonal matrix that's just the T matrix for this MTC. There's also a modular S matrix, and that needs to be a unitary non-degenerate symmetric matrix, and that encodes the braiding of two anions. So these two things, I'll draw a picture in a second, but these two things actually don't quite classify all MTCs. There can be MTCs with the same S and T, but actually have different what's called F and R symbols. So what are actually these weird operations? So the T operation is just you take a line, you loop it, and you stretch it back out, and you get some factor theta, and that's precisely this theta here. So that's associated with the spin. The S matrix is you take two lines, two anions, and you kind of link them, and they braid around each other, and then you sort of collapse it. It's all topological, and you get this factor of an S matrix, SAB, over S0B, where 0 is the identity line times the B line. So this is sort of basic T and S data for modular data. But then there are other things, the R and the F symbols. So F symbol is just like an associator, and the R is this move here. And these now have to satisfy certain consistency conditions. And this becomes an extremely complicated problem. So it's an algebraic problem. It's sort of very well defined, but it's extremely hard to solve, sort of starting at rank 1, 2, 3, 4. So one sort of approach to classify MTCs is, well, we just go in, brute force, put it into the computer, and try to solve these constraints. That's what sort of a long series of paper, many, many years has happened. And I think the latest paper is by Xiaogang Wen and collaborators up to rank 11. And at the moment, they're working since 1 year on rank 12. So this is sort of a huge collection of MTCs that they get in this way with all the S matrix, T matrix data. The second strategy is a bit more exotic. I mean, there are other ways to thinking about this, but the two remaining ones I'd like to discuss are sort of tied to geometry and strings. So one sort of very peculiar observation in this paper by Cho, Gang, and Kim a few years ago was you can take the 62,0 theory, put it on a three-manifold, and now you put this on a particular three-manifold that's not hyperbolic. If it's hyperbolic, one can show using the superconformal index it flows to an SCFT. If it's non-hyperbolic, their claim is this will actually flow to a gap theory. So it should be actually something like an MTC. Geometrically, the particular sort of compactification you have to look at here is you take the 60 theory and then you wrap it on an M3 that's a Lagrangian and a Calabi-Yau 3. And that Lagrangian needs to be a ciphered or a non-hyperbolic manifold. This works for, surprisingly, it sort of was an extremely interesting result. It works for 3 fibered ciphers and for the A1 60 theory. And it fails clearly, so just by tabulating all the possibilities for a higher rank, for r bigger than 4. But it's natural to ask, is there an extension of this? One can look at more general three-manifolds that are non-hyperbolic and for different algebras G. So we tried this, and this fails. But in the process, we kind of came to this point 3, which is a peculiar sort of association of three manifolds, so-called Seifert manifolds, and the choice of Lie algebra, to counting flat connections, and that counting of flat connections and the data on the Seifert manifold essentially defines an MTC. And there's a very sort of intricate relationship between the geometry of the three-manifold and the properties of the MTCs. And this actually reproduces, at least until rank 5, the MTCs in this gigantic classification table, and we're currently thinking about how to extend that. So 2 and 3 look seemingly similar, right? There's a three-manifold, but to our understanding, there's really no direct relation between these two things. Okay. So what is a three-manifold of Seifert type? So this is essentially data, so there are pairs of co-prime integers p and q. There are n many of such pairs, and they define something like a fibration of a circle over Riemann surface. And this fibration has sort of singular fibers, where we should think of it as at each singular fiber, we excise a disk, and then we glue in the solid torus of the disk times this S1 with sort of an SL to Z transformation defined by this P and Q data. So we basically glue it back in the circle with P times M1, M1 is this here, Q times L, this other circle. So in fact, these three manifolds are sort of a large subset of this Thurston classification of three manifolds, and you can have general genus G here, but actually for our purposes, we'll just have genus equal to 0. That's sort of another extension one could look at. Okay, so what is this MTC of M3? So I told you we'll have a three-manifold of the Seifert type. It's given by this PQ data, and we'll also pick some Lie algebra G, and then I'll define an MTC for you. So let's take SLN for simplicity. We can generalize this to ADE. And then the three-manifold has these PI-QI pairs. And then I define a tensor category that's sort of labeled by SLN, PI-QI, and then there's this sort of the linear product of categories, of tensor categories, and it's graded by the center of this SLN. So these building blocks are extremely simple. They're just some representation or subcategories or quotients of representation categories of quantum groups, U, Q, G, where Q is very well defined by this data P and Q. And this graded product is just saying these have gradings by the center of SLN. And in fact, if I take two graded tensor categories, I can define this graded tensor category, this product, which is just the sum here over all these graded tensor product factors. So this defines sort of one category. It has simple lines that are just products of the simple lines, modulo these relations from the grading. And in fact, they're labeled by sort of entries in the affine Weyl alcove of this SLN at some particular level P minus n. So for example, the simplest way to think about these building blocks is when Q equals to 1, that this is just Chern-Simons SLN at level P minus n. There's this grading by the one-form symmetry, and in fact, usually, so in this case not, but usually for generic P and Q, these are not actually modular, so they have degenerate S matrices. So what we'd like to do is now, this defines sort of an MTC. Now actually, why is this sort of an MTC that I should associate to a three-manifold of this type? So this is the connection. It comes from counting actually particular type of SLNC flat connections. So SLNC is this complexified group. So we're actually looking at maps from the fundamental group of M3 into SLNC. And to actually determine such solutions to this problems of flat connection counting, essentially it's useful to have a very nice representation of this pi1 of m, which In the case of cipherds, it's extremely simple. It's generated by some elements xk from 1 to n, so the n fibered cipher will have n generators and then one central generator h, and they have to satisfy these relations. So that's pi 1 of a ciphered manifold. And you can see that this depends on this PQ data. So we're not interested in all flat connections, but sort of irreducible flat connections. So it all means that basically these flat connections have finite stabilizer group. So the stabilizer group, the G's that commute with these flat connections, that's actually of finite size. And this actually implies a lot of simplifications in terms of what kind of flat connection representatives these H and these Xi have. So for example, the representation of H has to be just a grading, so it's identity matrix times some grading, where L is sort of going from 0 to n minus 1. So in fact, all these flat connections, these irreducible ones, are graded by Zn. And then in fact, in each of these sectors, we can diagonalize the remaining generators and then sort of try to solve these consistency conditions that come from this relation. So those are irreducible flat connections. And then that's actually still not enough. So if you just look at the irreducible flat connections, they don't define an MTC. We actually need to sort of specify one additional condition, and that's what we call anionic flat connections. And it just means that in this representation of xk, all the eigenvalues are actually distinct. So what it means in practice is that, so these row of xk's, there's some diagonal matrices with some labels ak. These lie in a particular interior of some wild chamber. So a cutoff wild chamber is in this wild alcove. So for example, for SLN3, for SL3C, this is sort of the two-dimensional plane of the fundamental weights. I can put p equals to 7, and then in this fundamental alcove here, it would actually sit in the interior, so just the points that sit in the inside. So those would be the solutions to this flat connection counting problem that are irreducible and are anionic. Okay, so the correspondence is now, well, we start with the geometry. We look at the anionic flat connections labeled by the Three-manifold. And in each sector L, there'll be a certain set of anionic flat connections. We can compute for these from the Chern-Simons functional, the spin. And then we can compare this to this tensor product of these representation categories of this UQSLN. And they carry also some labels here. And in fact, in each sector L, these will agree with these kind of flat connections. So given a cipher, so this is sort of basically the correspondence. You input a Three-manifold and G, in this case SLN, and then you will define an MTC. And in fact, the spins and also the S matrix will come from this particular evaluation of the flat connections on the Chern-Simons functional. It's not clear that this is actually consistent, that this hangs together. So a lot of this analysis actually is based on huge numbers of numerics, which we ran last summer. But there are some hints that there are sort of some interesting connections, there's some sort of cross-checks. The first thing is that there are some identifications between different ciphered manifolds. So if you have P and Q, P prime, this should be P prime, Q prime, they're related in the following way. The Q is just shifted by multiple of P, where the multiples sum to 0. Then actually the Three-manifolds are diffeomorphic. They're really the same sort of Three-manifolds. And so then you should actually check that the MTCs that we define this way also are the same. And that sort of checks out. So there's some kind of equivalences in the set of Three-manifolds that also translates into these MTCs. And then perhaps the most sort of striking thing is this product of these representation categories C is in fact not always actually modular. It's pre-modular, so it has actually a degenerate S matrix generically. And there's a sort of really nice connection between the topology of M3. So if H1 of M3 with coefficients in the center of this algebra G, so in this case Zn, is trivial, if and only if there's actually the S matrix is non-degenerate. So that tells you a little bit there's something non-trivial going on. The modularity is linked to some topological related conditions in this M3. Maybe so if someone actually knows this paper I mentioned in the strategy 2, this condition here is, for example, not imposed at all in their analysis, and so the association of MTCs to three manifolds is completely different. So here, this is really, the modularity is tied to this vanishing of H1. And finally, we can indeed, as I was telling you, we can indeed, for these anionic flat connections, evaluate the Chern-Simons functional. Technically speaking, it's only done for Seifert manifolds for SUN Chern-Simons, but then miraculously evaluating it on these flat connections for SLNC also matches precisely these box products of pre-modular categories. Okay, how much time do I have? 5 minutes? Okay. So I would just want to very quickly go through an example and show you how explicit this is. So this is an example that goes beyond the 3-fiber SU2 cases of the Korean paper. So GC is SL2C, the center is Z2, and we take a very simple three-manifold with P is 3 times, and then 1's 4. The Q's are all 1. And in fact, we'll show that this defines a rank 3 modular tensor category with the spins given in terms of this. There's a boson, there's a fermion, and some weird thing, and with spin 15/16. And that's how you see, so these anions are really different from standard bosonic fermionic lines. And then there's this S matrix here. So we'll get this from a graded linear product of the 3 factors for 1 fiber each. And in this case, sort of we can just construct each of these first 3 are just SL2 with P equals to 3, and this Q is given in terms of this power here. This is not particularly important. And then C4 is this last factor, which is given in terms of this product factor. So now we were saying that each of these actually are labeled in terms of these fundamental Weil alcoves, interior. So in the case of C1, 2, 3, these are just 0 and 1. And in terms of C4, there's 0 and 2. So these are actually the things that label the anions to the simple objects for each of these factors. Then each one has also a modular S matrix and an associated spin. So this is just a construction of this tensor product of categories. So once you actually evaluate all this, these are just 1/4 zero, so this is actually what's called the semyon, and this one here is the A12 theory. So looking at a graded product of these 3 times this here, this should be a 3 here. Okay. So now we take this graded product. The graded product says in each sector of Z2 charge either 0 or 1, what kind of sort of representations do we get? And we get precisely 3 representations, one in these 2 in charge 0 sector, and then one is in charge 1. And this 3-manifold has the property, that's something we can check for all Seifert manifolds, that the Z2 coefficient H1 is actually 0, and identifying now the spins and everything, this is one of these rank 3 theories, which succinctly is called 16, 639, 15/2, 4. Okay, so this is just telling you that with this kind of construction, you can now actually really reproduce these MTCs that with brute force methods have been obtained. If someone wants sort of a comparison to this Cho, Gang, Kim paper, I'm happy to discuss this in the questions. Okay, so now we can go ahead and could do this full classification. So basically, here is the rank of the MTC. So these are all rank 2, not necessarily unitary. These are also non-unitary MTCs. And this is the 3-manifold. This is SL2C. And this is the number of fibers. Some of these come from 3 fibers, and then some from 4 fibers. And this can go on until rank 5. And then we reproduce all these MTCs in this way from 3 manifolds. Okay, let me make some comments. So we check this until rank 5, unitary, non-unitary. And one sort of nice thing is that so each such MTC will have a 3-manifold associated to it, but that's not a unique sort of map. So not, given an MTC, you will have several different representations of it in terms of 3 manifolds, because there are also certain equivalences. One sort of very open question is, what's the interpretation, right? So we're just counting flat connections of a particular type on these 3 manifolds, and then we're associating three-dimensional topological order to it. Should there be a relation to the 6D story? This is not clear. So more conceptually, in terms of if you're interested in 3D topological order, why is this interesting? Well, it's complementary to the standard sort of representation of MTCs in terms of just Chern-Simons series. It's not even clear that all MTCs can be represented in terms of Chern-Simons series, so that's one of these open questions. One other nice thing is here, because the construction through the three-manifolds is a tensor product of extremely simple factors, we can actually also compute the R and F symbols. And those are usually very difficult to come by. So this is sort of one advantage compared to also this brute force counting, where usually there's just the S and T modular data. And then this also sort of has some intriguing connection between some invariances of three-manifolds and MTCs that's certainly worthwhile exploring more. So one challenge is really to actually explore to a higher rank and go to the type of models where no Chern-Simons realization at the moment is known, and actually see whether we can also get these from three-manifolds. Okay, let me thank you.